everyone. Thanks for joining us today. Today we'll be hosting Sarvesh, a third year PhD student working on theoretical aspects of reinforcement learning, mainly bandits and MDPs. He is an ex-student researcher at Google DeepMind, working on AI for social good, mainly only the use of restless and bandits in the context of maternity, health, and malnutrition. Further, he also plans to explore LLM alignment and multi-agent systems this summer at Adobe while working as a summer intern. His past interests include use of AI in sciences, mainly contributing towards astronomy and material science. Uh, if folks are interested in these lines, he would be like pretty happy to collaborate.
So yeah, I mean to start with, yeah, like I've kept my presentation really short, like around 8 to 10 slides. So yeah, like it would be great if it could be an interactive session wherein you can, like you can stop whenever you have any doubts or questions to ask. So to start with, so I will be presenting our work on RAI, also called as representative arm identification. And here we are kind of dealing in a multi-arm bandit setting, particularly in the context of fixed confidence. So what is fixed confidence? So it's like you want to kind of complete a particular task within a minimum confidence threshold. So it can be like any task to solve, and I give you error probability. So with that error probability, you need to like solve that particular task. So to start with, like what's this RAI problem? So say you have n arms, and all the arms follow a half subgaussian distribution. So in the context of probability spaces, half subgaussian distribution basically means a Bernoulli distribution, wherein the rewards are either 0 or 1, and each arm I has mu I. Each arm I basically gives the reward 1 with probability mu I. And say we have like m clusters. So before moving to what the cluster definition is, uh, like say say if you were known with the true means and you kind of arrange them in an ascending order based on the true mean. So then I say that say maybe top C1 arms belong to the first cluster, top C2 arms belong to the second cluster, and remaining say C3 arms belong to the other cluster. So in the diagram to the left, you can see like I have C1 equal to 4. That is the top 4 best performing arms are in the first cluster. Then the second best 4 are in the second cluster, and so on. So this is kind of denoted by the vector C, and this is a priori known to the learner. And the task basically is to identify some RG arms from every cluster. So in the given example, you need to identify 2 arms from the first cluster, 2 arms from the second cluster, and yeah, just 1 arm from the last cluster. Now, talking about how this problem motivates, it comes from the context of crowdsourcing. I'm not sure if you guys are aware about Amazon Mechanical Turk and similar platforms, but there basically say you want to annotate some data and you need public volunteers to do that. So you kind of upload your data there, and there are people providing services by volunteering to annotate your data. However, you need to kind of give some monetary compensation to them. So say like to classify a particular data set, you identify that if you want to keep the cost to be minimum, you need to identify you need to get it labeled from say 2 best performing people and 3 say medium performing people. So how to do that optimally is what this problem will help to solve. And secondly, this also happens to be a generalized formulation covering multiple standard bandit setting. So to the left, you can see a standard case of best arm identification. So in best arm identification, you just need to identify the best performing arm, and it's widely explored in the bandit literature. So if we want to kind of adapt our problem formulation to the BAI problem, then you just have to consider C1 equal to 1 and say C2 equal to n minus 1, and you just need to identify arms from the cluster 1. Similarly, to the right, you can see there's something called as M out of top K arm identification. So say you have say n movies or say you are watching Netflix, and Netflix folks want to kind of recommend you a few genres of movies which you would like to watch. So based on your previous history, say there are total of n genres that you have watched until now. So out of the top five best performing genres, that is the top five type of movies that you have watched, the Netflix folks want to kind of recommend the top two or maybe any two out of top those five. So yeah, like so basically, this particular problem kind of specializes to uh, various problems in the standard bandit literature and kind of covers the entire space of uh, bandit problems. Are there any questions in the problem formulation? Sure, maybe I can go ahead.
Uh, do you have both the settings over here?
Sorry.
I mean, you just said, you talked about best arm identification
Yeah.
and amount of top K arms identification.
So
Do
what
you
I'm
have,
saying is, yeah, go
yeah,
on, go on, go on.
yeah, sorry. No, I'm just asking, like, uh, is it the one problem you're talking about? Are you talking about both the problems?
No, so I mean the RAI problem that we kind of formalize in this work, it can be specialized to multiple standard bandit formulations. So whether it be best arm identification or say top K arm identification or M out of top K or even like worst arm identification. So with appropriate definitions of CIs, that is cluster sizes, and RIs, that is required number of arms from every cluster, you can formulate it to any of the standard bandit setting.
Okay, makes sense.
So
Thanks.
like to the left, you can see I have 10 arms and I just consider C1 equal to 1 and C2 equal to 9. And I
Right.
just ask the learner to identify one arm from the best cluster. Then the problem gets formulated as a standard best arm identification problem.
Mm-hmm.
Similarly, towards the right, say we have 10 arms again, and we need to identify two out of top five arms. So in that
Right.
case, I have like C1 equal to 5, that is size of cluster 1 equal to 5 and size of cluster 2 equal to 5. And from the first cluster, we need to identify two arms, and from the last cluster, we don't need to identify any of the arms.
Right.
Is it clear?
Right. But among these two clusters,
Sure. Yeah.
how are you actually choosing the right cluster? Is it based on rewards?
But yeah, so I mean, to the left I have 0 and to the right I have 1. So the arms in the diagram are kind of arranged in the ascending order. By that I mean this arm has the lowest mean. This is the arm with
Uh,
second lowest mean. This is the arm with highest mean, second highest mean, third highest mean, fourth highest mean.
okay.
So basically, like arms with yeah, top five arms, that is based on the reward, are considered in first cluster, whereas the worst performing arms are considered in the last. But yeah,
Okay.
like this is what learner has no idea of, like
Right.
which arm will belong to which cluster, and that's what the task is, to identify a required number of arms from the specific cluster.
Right.
So yeah, so basically, like we give a learner 10 arms. We tell it that the cluster sizes are 5 and 5, and we
Right.
ask it to identify two arms out of the best cluster.
Okay.
And yeah, is it clear?
Yeah.
So moving forward, similar to like any standard BAI literature or any standard bandit literature, we start with we start by defining a lower bound to this logic. By lower bound, it just means that no matter whatever algorithm you use, it will take at least this many pulls to identify solve the problem with a particular confidence. So again, the derivation is kind of pretty simple. If time persists, maybe I can go to it. But the whole idea here is uh, to kind of interpret this lower bound, you can simply consider the best term identification problem. So as you see here, you have like one arm in the first cluster and remaining n minus one or 9 arms in the second cluster. So here the bottleneck gap that we define as delta I, here mapcal I is basically an instance that is specified. So then for the best time identification case, uh, the capital delta I will basically be distance between these two arms. That is mu1 minus mu2. Similarly, if you have happen to talk about m out of top k, then it will just be like, for this particular case, it would be mu2 minus mu6. So intuitively, it's just that the easiest or possibly like in the best case, which arm will be the last one to kind of be identified is what the bottleneck gap kind of captures. So based on that formulation, based on this notation, we have this lower bound to this particular problem, that is expected time or expected number of pulls is kind of lower bounded by 1 by 2 delta I square times log 1 by delta, where again delta is like the error parameter. So here we say that with at least probability of 1 minus delta, the algorithm or we solve the problem. Yeah, with at least probability of 1 minus delta. Uh, so yeah, are there any questions related to this slide as such?
Uh, so you're talking about the variance? What is
No,
it?
so variance
Error,
is fixed. Like,
error threshold.
so what I'm saying is, so are you familiar with the fixed confidence setting?
What do you mean by that? I just know UCB.
Okay, so what I mean is, so as I defined the RAI problem before, so
Right.
the task is basically to take as many pulls as you want, but the given answer that the algorithm or that the learner will give me should be correct with at least probability of 1 minus delta. So as delta tends to 0, my confidence tends to
Gets
like
yeah,
1.
10 to 1.
Yeah.
Okay.
So yeah, that's what basically the fixed confidence setting means. And what this lower bound states is, if you want to identify, uh, or you want to solve the problem with probability of 1 minus delta, then you will require at least this many pools. So
This many
that
pulls.
pools are kind. Sorry.
Okay. This many pulls. You mean arm
Yeah.
pulls? Yeah, makes sense. Okay.
Yeah. So
What's the C here? Yeah,
uh, you
the
mean this
C1.
C?
The C1, C2,
Ah,
and C3.
so these are the cluster sizes.
Okay.
By that I mean C1 is basically top C1 arms. C2 is
Mhm.
like top C1 plus C2 arms excluding C1.
Okay.
Or you can say next top C2 arms after C1.
Right.
Yeah. And then we move to some delta PC algorithm. So PC here stands for probability correct. So here, I mean, the algorithms are kind of very simple, I would say, and are motivated from the ideas of confidence bounds. So uh, the the algorithm, the pseudocode of the algorithm basically looks very simple and just involves pulling every arm in round robin fashion. And at every time t, we basically check for a certain criteria. If that is met, then we kind of stop pulling that particular arm. So
Mhm.
to move into its details, like at every say you have n arms, or yeah, say you have n arms with you. At every time you pull like all the n arms, so corresponding to that, you have empirical means with you, denoted as mu hat 1 to mu hat n, right? And then based on the number of times you have pulled the arms, you kind of have some confidence interval on it. So by that I mean, if mu of I is this thing, okay, then with some probability, I am sure that my empirical probability lies in this particular range, like between in this particular box. So to simplify, I'm not sure if you guys are aware about Hoeffding's inequality, but these ideas are kind of motivated from the confidence from the so-called concentration inequalities. So at every time t, after we pull all the R's, we check for a certain criteria, which is whether the lower confidence bound for that particular arm is separated from a particular number of, I mean, UCBs of a particular number of arms. So here UCB stands for the upper confidence. So to give you an example, these two arms are not separated because the LCB of this particular arm, that is this line, does not overlaps with UCB of this arm or of this arm. So if it would have overlapped, then we could have commented that we would have been sure that this particular arm does not belong to the last cluster, because then we would have at least two arms which are performing bad than this particular arm. Similarly, if you have to talk about this particular arm, so I know that the else, sorry, actually, it will go vice versa. So here the LCB is greater than UCB of the last worst arm. So that's how we know that this particular arm won't belong to this particular cluster, and this particular arm won't belong to the second cluster, because there are at least um, 8 arms that are performing better than this particular arm. So either it will be this arm or the second worst arm in this third cluster. Similarly, here you can see that there is an overlap between LCB and UCB. So if this were the empirical estimates, then it's possible that I'll just zoom in here. Okay, I'm unable to zoom in. Can I annotate on the screen?
Yeah, I think so.
Yeah.
You can.
So yeah, so if this was like say mu hat I, not sure if, and if this was mu hat j, then it could be possible that mu hat, sorry, mu j belongs here, and mu I belongs to this particular region. So given that there's uncertainty associated and we can't surely comment about the identity of ith and jth arm, like we have to kind of pull these arms like a more number of times, and the given number of pulls are not yet sufficient to comment on the identity of the arms. On the other hand, here mu I could, if this was say I and this was say j, then we know that the worst mu I can be is here, and the best mu j can be is here. So we know that there are at least 8 arms, that is this many number of arms that are performing better than this particular arm. So that's the that's the idea of a typical round robin type algorithm. And in addition to that, let me hide this pen. Yeah. So, however, like for the center clusters, we kind of need to comment on the LCB as well as the UCB part. That is, if we want to say that this particular arm belongs to, oh, sorry, this particular arm belongs to the second cluster, then we have to comment that the UCB of this arm is less than the LCB of every arm in the first cluster, and LCB of this particular arm is better than the UCB of all the arms in the second cluster. And so yeah, this is how our vanilla algorithm goes on. However, like there are some complications, or you can say some additional complexities that kind of get introduced here, due to which our upper bound, our upper bound or on the sample complexity is kind of looser in nature. So to kind of avoid that, we do a batch sampling. So in that case, like we pull all the arms specific number of times, which is kind of in the exponential parts of twos. And after we are done pulling all the arms a specific number of times, then we kind of uh, check for this particular criteria, whether like LCBs are greater than UCBs and UCBs are greater than LCBs. So you can see towards the right that in the vanilla algorithm, wherein we check this so-called LCB UCB criteria at every time instant, we have an additional, and towards the bottom we have the complexity for the butterscotch algorithm or the batched sampling algorithm. So here you can see that the complexity has like ln of ln 1 by delta I. On the other hand, here you just have ln 1 by delta I. So there's an improvement of logarithmic factor if you happen to use a butterscotch algorithm over the vanilla algorithm. However, again, like empirically, there are some limitations in the butterscotch algorithm, because you pull all the arms a specific number of times. So that we will see in the further slide. And in addition to that, we also introduce merging subroutine. So why is it needed? It's because like if you identify a respective number of arms from a particular cluster, then giving more pulls from the arms from that cluster is basically just waste of pulls. So say for example, if you want to identify, just consider this particular example. You want to identify two arms from the first cluster, two arms from the second cluster, and only one arm from the third cluster. So say the algorithm kind of identifies the one arm from the worst cluster and two arms from the center cluster. Now, if we wouldn't have avoided this merging, then for this arm to be eliminated, it would have been separated with this arm, which will take significant amount of time. On the other hand, given that we have already identified the required number of arms from the last two clusters, we can kind of merge these two clusters, and to remove this particular arm, it will kind of be compared with this particular arm, that is fourth arm, instead of like eighth arm in the instance. So that's how basically there's an empirical improvement in the sample complexity. We can also see it theoretically, but writing that expression is kind of, it will become complicated to write that expression. However, it's like very simple if you have to think it intuitively. And here, like, while I give an order-wise notations, that is T delta I is order-wise proportional to K by delta I square ln n by delta I. We do have a proper closed form solution for this, along with the instance specific constants. So those are kind of added in the paper here. Maybe, yeah. So yeah, the expressions are kind of very complicated to interpret. So that's why I just add an order-wise expression to comment on the complexity.
Are
Yeah.
the clusters here defined specifically on the basis of some like a particular
Yes, sir.
threshold? Yeah.
No, not really. So, I mean, there's no threshold here, but we say that top four arms are in first cluster.
Okay.
Now,
Okay.
I don't know, like, it could be like in top four arms, I have arms with mean like 0.9, 0.8, 0.7, 0.6, or it could be like 0.9, 0.95, 0.90, 0.85.
Mhm.
It could be anything. It's just that you can say like it's percentile wise stuff. That
Okay.
is top top four arms are basically in first cluster. That is, 40%. Yeah, top 40 percentile is in the first cluster.
Okay.
Then next 40 is in second cluster, and the remaining 20 is in the last cluster.
Could you also highlight the sample complexity, like your butterscotch algorithm
Sorry.
versus the? Could you highlight the sample complexity here, like the butterscotch algorithm that you have? I think so. In the paper, you also have a butterscotch round robin algorithm.
Yeah.
Yeah, representation. So, like, will you be covering that in the future slides as well?
No, not really. Like I didn't add it in slides as this. I mean, this is like a complicated expression, I would say, and would be kind of hard to interpret. So, I mean, the whole idea is that the smallest gap that we see is basically the bottleneck gap
Mm-hmm.
in complexities of both the algorithms. So, I mean, that's the kind of whole, what you can say, the idea of the complexity or the idea of the tightness. So, however small or however hard the instance may be, uh, you will see like the bottleneck gap to be the smallest gap in your upper bound as well as the lower bounds. And that's how we define. That's how we define if the algorithm is tight or not.
Yeah, I think so. It's inversely proportional to the square of the bottleneck
Yeah.
gap here.
Yeah,
Yeah.
yeah. So here you can see it's inversely proportional to, it's directly proportional to 1 by delta square. And in the lower bound also we have like directly proportional to 1 by delta square.
Mm-hmm.
By delta, I mean delta math कहलाए, that is the bottleneck gap.
Yeah.
So, and again, like, why do we have a specific improvement in the butterscotch algorithm over vanilla is because of the fact that we're not checking the separation criteria at every time step. So due to that, we kind of have a relaxation on the union bounding that we need to do. So in the former case, that is in case of vanilla algorithm, we need to ensure that the empirical mean lies between some mu plus alpha and mu minus alpha at every time and at every and for every arm. So in that case, I have like summation on that probability. I'll just show if there's an expression here. Mhm. Uh, Yeah, so I need to ensure that this particular quantity, I'm unable to, which I have highlighted. This ensures for every arm and for at every time t. So due to that, I have like a loser confidence bound. On the other hand, given that in butterscotch algorithm we only check at exponential time steps, I kind of have a tighter bound there. So due to that, uh, if we have to comment on theoretical aspects, the butterscotch algorithm performs better than the vanilla. And the more the number of time steps that you increase, the more better the algorithm will perform. So in this particular case, given that we are doing an exponential power of 2's, here we have log of 2. So if I had done like exponential power of 10, then I would have like log of 10. If it was 100, then it would have been log of 100. So so the reason why butterscotch algorithm performs better than the vanilla in case of time complexity is because of the relaxation in the union bounding, which kind of results into a tighter confidence bound across arms. Am I clear here?
Yeah, I think so.
I mean, if still there are doubts, and probably it could be like, if these are at particular time t, if these are the bounds for vanilla algorithm, then this will be bounds for the butterscotch algorithm. Butterscotch. So because of this tightness of the bound, it kind of happens to perform better because it will eventually identify the arm immediately compared to the vanilla version. But yeah, like as I said, here you're doing a here you're doing a particular number of pulls. So say for example, if your instance was like say you had like two arms. One arm had like mean of 0.99, the other arm had like mean of 0.01. Then you wouldn't really need to do some exponential number of pulls to identify the arm with mean 0.99 is the best arm. So that's where the butterscotch algorithm lacks, and that we also see from the sample complexity. So for example, here like we need to just, so these are the empirical performances of our algorithms, and we have some baseline called as LUCB. So I'm not sure if you guys are aware about LUCB as such, but LUCB in standard BI setting pulls two arms at every time. So we kind of adapt the standard LUCB to our problem formulation, and we obviously ensure that it is delta PC algorithm. However, we don't derive an explicit sample complexity proof for the LUCB algorithm that's what not our focus was. But yeah, as I was saying, the like if you want to identify one arm from the top cluster, that is so if this was the instance and you just need to identify this particular, instead of this green thing, if it was like this, then that's what the instance here means. And in that case, you can clearly see that LUCB performs the best. So it's because of the sampling rule on how LUCB is defined. And on the other hand, like while butterscotch has a better sample complexity than the vanilla algorithm, so again, like to note that these are the worst case complexities and not the expected bounds. So yeah, while the worst case bounds are kind of better for the butterscotch algorithm, vanilla here performs the best because like in this particular setting, the butterscotch algorithm pulls all the arms around 1,000 number of times before checking the stopping criteria or before checking the identification criteria for every arm. So while we see a theoretical improvement over the complexity, if you have to talk about empirical performances, in some cases, vanilla algorithm will perform better than the butterscotch. On the other hand, if you see the second example, that is identifying the complete top cluster, then butterscotch algorithm performs the best, followed by vanilla LUCB. So, I mean, if you have to draw kind of summary from here, then the baselines such as LUCB or say any UCB kind of algorithm will kind of perform better than these baselines, better than these algorithms in the cases where you need to identify like lesser number of arms or the instance is kind of very easier to solve. So for example, in the best arm identification case, I would expect LUCB to perform better than vanilla and butterscotch algorithm, unless like the instance is very, very hard. But on the other hand, if you want to do some coarse ranking kind of problem, that is identify all the arms from every cluster, or like identifying top cluster or any complicated problems, then LUCB or UCB-type algorithms will perform relatively bad or relatively worse compared to this algorithm. And then we comment on the effect on empirical performances due to the merging subroutine that we had introduced here. So if we wouldn't have done merging, then the vanilla algorithm would have taken around 6,491 pulls for this algorithm for this problem to be solved. But given that we are doing that, it takes around 4.5k pulls for the algorithm for the problem to be solved. The same improvement can be seen in the case of butterscotch algorithm. However, like as I said, the butterscotch algorithm in the first instance pulls all the arms around 1037 number of times. And given that we have 10 arms, there are a total of 10,370 pulls. There's no really change uh, in the complexity due to merging or non-merging. However, on the other problems, you can see a clear improvement after we introduce the merging subroutine. And then, like, yeah, this was some synthetic. Yeah, so before moving forward, do you have any doubts here?
Go ahead.
Uh, shall I move forward?
Yeah, sure.
Hello. Hello, can you hear me? Uh,
Yes.
yeah. So yeah, I mean, this is one. I mean, yeah. So here, like, we do some experiments on synthetic data, but yeah, like, you can always have synthetic data. Like, you can kind of generate synthetic data as you wish. Like, there's no really point of showing all the performances on the synthetic data. It is like the best way to intuitively tell on when your algorithm will perform the best and when it wouldn't. But it's not something which like anyone would prefer on to compare with. So we then move to some real world data set wherein we query the so-called popular movie lens data set, and like to keep this experiment very simple, we kind of only consider 50 movies with the highest number of ratings. And if you want to kind of map this particular problem to the bandit literature, then here movies are basically treated as arms, and the reward corresponding to every movie is basically what the user has rated it. So in the data set, the movies are rated on the scale of 0 to 5. So we kind of normalize it by dividing it by 5 to have a Bernoulli, to have it mapped to the standard sub-Gaussian, or yeah, to the standard, yeah, to our setting basically. And yeah, here basically pulling an arm is just selecting a movie. So you select a movie, ask a user to rate it, and that's what basically your reward is. And on that particular data set, then we uh, yeah, then we check our algorithm as to how it performs. So you can see for best movie identification, that is a typical BAI or best term identification problem, the LUCB algorithm performs better than all the other algorithms, include that is vanilla and butterscotch. And in addition to that, we can see like butterscotch performs better than the vanilla on this particular given data set. On the other hand, like for M out of top K movies, so here, like yeah, there's one thing missing, that is I have not mentioned what is M and what is top K. So uh, so K is basically the 50% of the total number of movies considered. That is, in the first image, like K will be 5. In the second, K will be 10. In third, K will be 15, and so on. And similarly, M is like 30%. That is, in the first case, M is like 3. In second, it's 6, and so on. So say you want to identify 2 out of top 5 movies out of 10 movies, then you can clearly see that butterscotch algorithm performs best, followed by the vanilla and then the LUCB version. Similarly, in the case of 20, 30, 40, and 50, like see a similar trend, that is butterscotch performing better than the vanilla and vanilla performing better than the LUCB version. So that's what basically our hypothesis was, based on the synthetic data sets as well, like for easier tasks such as identifying top arm, or identifying one arm from the top, say 5 arms, or one arm from the worst cluster. LUCB kind of performs better than, or LUCB is kind of expected to perform better than the vanilla and butterscotch algorithms, unless like the instance is like very hard to solve. But otherwise, yeah, and this complicated problem formulations where you need to identify top clusters, or you need to do like full ranking, or do some coarse ranking. There you see a better performance of the vanilla and the butterscotch algorithm compared to the standard baseline, that is LUCB. So yeah, and that's it from my side. So if you guys have any doubts.
So on the paper, you also had have a section on federated performance.
Section on?
Federated performance. The
Sure.
federated, yeah.
Yeah. Yeah. So I mean, so in federated setting, federated, if you have to do over this work, then it will just be an incremental work. So we don't really have that federated section here. But the idea is, say you have M clients with you. Okay, so M clients kind of solve individual problems at their end. That is, like, client 1 may want to identify just the best term. Client 2 may want to identify the full cluster. Client 3 may want to identify, say, one out of top 5 arms, and so on. So, like, all the clients will have independent problem to solve. On the other hand, like, there's some global problem to be solved. That is, yeah, fine, there are n arms divided across m clients, and every arm in this particular client performs like this. But how does it perform globally? So for that, you have some centralized server that every client reports to, right? And the reporting, and there will be some cost that your algorithm has to incur while reporting, while doing this reporting. That is, doing this, like, by that I mean client reporting about the instance, about the current scenario of the instance to the server. So in the federated setting, basically your task is to minimize the cost. So by that I mean minimize the number of pools, as well as minimize the communication cost that your algorithm will incur. So there, a combination of butterscotch plus vanilla algorithm will kind of suffice, as the whole idea will be to kind of communicate. So the whole idea will be that all the clients communicate with the server at exponential time steps. On the other hand, in their particular client specific settings, they kind of check for this stopping rule at every particular time. So given that you have this exponential stuff going on in this particular setting, the communication gap will be very minimum. And that's how basically this particular problem can be solved in in the federated setting. I mean, if you are interested in those lines, you can check uh, work by Vincent Tan. They do like best term. They only comment on best term identification in the federated setting. So they have like this exponential time stuff in their paper, so as to minimize the communication cost.
Cool, thanks. And so in the real world implementation in the recommendation settings, for example, so how does this
Sorry?
in the real world settings and the recommendation setting in the recommendation algorithms, so how well this perform?
By recommendation, you mean like something like Netflix type stuff?
Kind of. There are many recommendation algorithms available, like music service, movie service, or any
Yeah,
other. Yeah.
yeah. So movie lens is like the data set that is kind of similar to what you mean.
Hmm.
So you have like 50, you have like say like you have n movies, and corresponding to all those n movies, you have a user rating.
Hmm.
So say if I have to like recommend you a particular movie, then based on your past history, I know that you kind of prefer this genre of movie over say X genre of movie over
Yeah,
Y
yeah,
genre of
I get that, but you haven't
sure.
included the top benchmarks for like the butterscotch versus the vanilla and the LUCB. So you kind of haven't got the top of the line, the state of the art uh, algorithms that are used currently or that are open source. So maybe kind of a suggestion here is to compare with them and add a table as to where your algorithm kind of stands in the whole set.
Oh, sure, but I mean, I don't get how do you relate it to this particular setting? Uh,
It will be kind of like beneficial to gauge an interest as to how multi-arm bandits like perform the best of the multi-arm bandits or your specific algorithm perform with respect to how in the recommendation
okay, sure.
yeah.
Yeah,
So
yeah,
like if someone is trying to build a recommendation service from scratch, maybe on
sure.
any of that. So like and any of the downstream like product recommendation stuff that you can have. So he or she may like work on that or compare your with like the SOTA models and like
Okay,
come up to a conclusion with respect to the advantages and the disadvantages of each and everything. So from an application point of view, that's
okay,
yeah.
sure. Yeah, thanks. Yeah, check it out.